I usually like a doctor. What if the name is Jerry?
All right, let's talk. Let's talk about the quiz a little bit here on Monday. Now tomorrow I will not be here for a good portion of class as we leave for Omaha for basketball. So I'll be here for the first little bit, 10, 15 minutes or so. So we'll get a lot of things. What I'll probably do is record second block. So in case you wanted to look at it, it'll be work time for you guys, especially in second block when I'm here. I'm sure I'll be answering some questions. We may go over a few things that I may not get to. Kind of depends what the questions are. So I'll record that during the second. So if that's something you want to look at over the weekend, quiz is going to be on Monday. Okay. So we have a variety of things. Just there's nothing new really. So it's more a matter of giving you some work time. So we're going to have some work time today too. So letting you work and think through those things and talk about them and so forth and help each other out and ask questions of me. So so the quiz is over 4, 3, 4, and 5. Okay, sections in the book. So section 4.3 was the optimization. So on the well, then I just close that out. On our class website, I've added a couple of things here that may be of interest, possibly. The all right, down here in the section on homework and assignments, I have put for today, we're going to get a new packet. We're going to get several new things here. This is from another textbook. The business packet's from a textbook. This is from another textbook. The author is named Anton. And so this is the Anton packet. Or Antone, or I don't know how you pronounce it for sure. But so I've got a copy of that packet, but you'll get that. And I've got also some worked out answers, just like with the business packet. I also have notes from last Friday, which were the notes we took those were the notes we took on optimization. That also had the parametric equations in here, here. So if we let me scroll down. So the parametric equations, there was the optimization kind of stuff. I've also got a PDF here of related rate hints. I hadn't showed this before. This is just kind of the steps maybe in related rates. If you identify the various amounts and rates in the problem, draw and label diagram, write an equation that relates the various amounts, differentiate both sides with respect to t, substitute the given values and solve, and check your answer for the correct sign. And then I've also got, if I can grab it, let's do it here. I've got the ladder one kind of worked out there. Got a cone one kind of worked out here. So those are all accessible for you on the website under Thursday's assignment sheet. So those things are available too. Okay. So let's talk about the homework and then the parametrics. And I've got an example of a parametric equation. Again, you need to be able to graph a parametric. It'll be all calculator, the whole quiz will. You need to be able to graph one on your calculator, sketch it on your paper. You need to be able to mark the direction of travel. You need to be able to trace maybe and label some points on your graph. You need to be able to do the speed of a particle, know that equation, know the slope of the path, those kind of things when it comes to parametrics. So those are kind of the main things on the quiz. And somebody was asking the other class, he says, is this the hardest thing we do this year, or is it going to get harder? It's kind of hard to answer that, but it is. I would say this is one of the harder things because of the having to set up these story problems, right? Having to get the equation set up and so forth. And everyone's kind of different. It's not like you kind of memorize these certain facts. Even though we have some steps to follow, it's like each problem kind of brings its own thing to it that you've got to be able to work through and figure out. So from that standpoint, I think historically it has been one of the more difficult things. So I guess that's bad from one hand, on the one hand, and but once you get through it, maybe that's good, a good thing. So anyway, let's do the swimming pool problem here. I've drawn it to help you a little bit with the picture here. What issues did you have with the swimming pool problem? Let's approach it that way. What were some things? Where did you get stuck?
First, I was thinking that there might be like some equation that would like apply to the entire, like both parts of the problem, which wasn't the case.
Oh, the whole pool. Instead of splitting it, yeah, it's really a case where you got to kind of split it into this triangular wedge shape, and then the box shape up here, right? And so coming up with a volume equation for that, right? And so that's why there's two parts in this problem: the 2,000 cubic feet and the 3,000 cubic feet part. Let's take the bottom section of the pool only. What's the volume formula for the bottom section of the pool? It's just half of a box, right? So it's just half times length times width times height. And so on your calculator, you could take 1/2 times 40 times 15 times 7, because it's 7 up to there, and then it's 3 there. So what's 1/2 times 40 times 15 times 7? 2,100. So there's 2,100 cubic feet of space in the bottom part of the pool. So when they say find the rate that the water's rising at 2,000 cubic feet, the water is still in the bottom part of the pool. Now, imagine this scenario. The water is pouring into the pool, so the water level is rising. In the beginning, what's the water level rising compared to later? The rate. It's faster in the beginning, right? Because in the beginning, it's this small little area, this small little piece, so it's going up pretty fast. But then as it spreads out this way, it slows down. So if you were going to draw a graph of that situation of the volume of water, not the volume of water, but the rate that, the height in the pool, it would be going up, but it would be leveling off, right? Because it's going up slower. So it's going up pretty fast in the beginning, and then slower, 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 slower. And then what about when it gets up into here? Constant. Once it gets up into here, because the water is coming in at a constant rate, so once it gets up in this top part of the pool, it's just going to be constant. Okay? All right, so that's helpful in just understanding the situation. So the 2,000 cubic feet part, so when the volume is 2,000 cubic feet, you know it's going to be down in this bottom section. So that's why I've drawn the blue here. All right, now in the blue picture, this we don't know. So I'm going to label that X. And this we don't know. In other words, it's changing. I'm going to label that Y. Now what about this back here? Always 15. So in this blue wedge, or half of a box of water, the volume is going to be 1/2 times 15, so that'd be 15 halves, times X times Y. That is the key to getting this set up, is the blue half of a box of water would have that volume right there. Now, in a related rate problem, it would be okay to do the derivative. The problem is we have V prime, X prime, and Y prime. Now we know V prime, they told us that was 25. We're trying to find Y prime. The problem is I don't really want an X prime in there because they didn't give me any information about that. It's kind of like a cone problem where we want to get in terms of fewer variables. Now in optimization problems, we always do that. We always want to get it in terms of one variable. But in these problems, we don't necessarily have to. But on the cone one we do, and on this one we do too. And so this is where the similar triangle comes in. If you look at this big black triangle here, and then compare it to this blue triangle here, you've got a ratio. X over Y is the same ratio as 40 over 7, because this is 40 right here. So 40 over 7 and X over Y. And so now I can solve this for X, so I just multiply the X over there, and I get 40/7 times Y. And then I want to plug that into this equation over here. So if I take 47ths y and put it in for x, right? So I take 47ths y and I stick that in there for x. Now I get something like 300 over 7 times y squared. Does that look familiar? Something like that. So now I've got that volume of the water as being that. And now I can do my derivative. Okay, now even then there's still a little piece of this that gets kind of interesting. So v prime, I bring the 2 down in front, so that's 600 over 7 times y, and then tack on the y prime. Okay, so they tell me v prime is 25. The y I don't know. Y prime is what I'm looking for. Now, I don't know what y is, but can I get it? What else did they tell me? Right here. The volume of the water is 2,000. So can I take and put that right there? Right? The volume of the water is 2,000. I can put that right there and I can solve for y. Now, just looking up in the answer book, that comes out to like, let me see. That comes out to y being like 6.83 something. Now, you might not change it to a decimal, but it's like 6.831 is what y ends up being. And so now you can solve for y prime, and then the answer, they've got a couple different answers here, but as a decimal, that might be the easiest to compare. And this answer book was wrong. I had to actually correct this, but 0.042695, and that would be, what was that in feet per minute? So that's what it ends up being. Okay. So part of that was different. I mean, if we compare that to what's going to be on the quiz, there was parts of that were more difficult just because it's this odd shape we're not used to working with the half of the box kind of a formula. But it's a lot like the cone with the similar triangle and be able to make that substitution. And then it was a little easy. They could have made this easier by saying, how fast is the water level rising when there's 6 feet of water in the pool, 6 feet deep? Well, then you could have just put your 6 in for y. But there's a little added difficulty there, and they told you the volume was 2,000, so you had to go back to your other equation and find y. So, but we should be able to handle it. All right, then the other part of it with the 3,000, now see, once the water's up here, now it's not as big a deal. Okay, because once the water's up into here, now we can just not even worry about the bottom part, and the volume is now just 40 times 15 times y, right? What's 40 times 15? 600? So v is just 600 times y, and then when we do our derivative, v prime equals 600 times y prime. Well, now, I mean, that's it. I mean, it's very easy. The v prime was 25. So we divide 25 divided by 600. We don't even need the 3,000. We only have to use that other than the fact we know when there's 3,000, it's up in here. And so it's just 25 divided by 600, which is like 0.0416 repeating. Which kind of makes sense with the other answer we got. Okay, there's only one variable now because when the water's up in the top part, the width and this 40, they're the same. So that makes sense because we said the water was going faster down here but slowing down. And so look what we had, 0.402 when it was up here, and then once it gets to here, it's 0.0416, and then it just stays constant the rest of that time. All right. And then let's talk about 23. 23 was this one with the cone. But what was difficult about this one? Yeah, it was a weird question that like we're not used to seeing. They wanted to know the ratio of the height to the radius. And so let's talk about cone problems. Normally, well, the easiest cone problem would be this kind, like we did yesterday, where they just tell you the radius is twice the height. That's the easiest one. Because now you take your cone equation, which is v equals 1/3 pi r squared h, Now you just take your 2h, you plug it in for r, you simplify it, now you're down to one variable, do your derivative, and away you go. You plug in your numbers and you find what you need. Okay? So that's the easiest kind of cone problem. The second easiest, or the next level of cone problem, probably the most common, well, about like this one, is where they just give you the size of the cone. So we did a problem like that where they said, well, the cone, the radius is 4 and the radius is 4 and the height is 16. So now you just set up your ratio. So you say, okay, the h over r is 16 over 4, right? And now you can solve that, right? You can get that r is equal to, what would r be equal to? 1/4 h, right? You could solve that, and r is equal to 1/4 h, and then you plug that up in here for r, and then away you go. So you've got to set up your own ratio here, okay, if they give you the size of the cone. In this one, they wanted to know what is the ratio of h to r. And so here's what was hard about this, and here's the part you probably would not think to do. Name that. That thing you're looking for, give it a name. Let's call it k. Because it is a constant, right? Think about this. That's what we've said over here. In these cones, as the water fills up or the water drains out, the height and the radius stay in the same ratio. So h over r is some constant. So you might think, well, that's silly. Why would I want to introduce a new variable? It's not a variable. It's a constant. So this is what they want us to find. So let's just find k. All right, well, if h over r is equal to k, now we can do what we did over here. We can go ahead and solve this. So r would equal, if I multiply r over there and divide by k, I get r is equal to h over k. Now let's take that and substitute that in there. So now my volume is 1/3 pi, and in place of r, I got h over k squared times h. Now again, like I say, you haven't seen that before, so you probably would not have thought to give that a name. But the key is that it's constant. Watch what happens now when I work a little algebra on this. This would be 1/3 pi, this would be h squared over k squared times h. Now, 1/3, constant. Pi, constant. H squared, variable. K squared, constant. H, variable. So let's gather the constants all over in the front. So this would be pi over 3k squared. All of that is constant times h cubed. And what do you do with a constant when you do the derivative and it's multiplied? You just leave it hanging out in front, right? So the pi over 3k squared just stays there. So now I'm going to do my derivative. And so I'm going to leave this constant just hang out there. I'm going to bring the 3 down in front. That'll cancel that 3. So I'll have pi over k squared. Derivative of h cubed then becomes h squared. And then I tack on h prime, right? So it's all in the algebra at this point. While thinking to do this, then in the algebra and saying, hey, k is a constant, so I can just pull it out. And now we got this, and I think they gave you all of those numbers in, didn't they? What was v prime? Good. It is negative. That's right, because the volume is decreasing, so you need to put a negative on that. The pi over k squared is, k is what we're trying to find. What did they tell you h was? 8. Height was 8. And then what's h prime? -2. And so there you go. And so now you have everything but k, and k is what you're trying to find, because k is the ratio of h to r, because that's how we set it up. So that was kind of a strange one, and you're not going to see something like that on the quiz. But you know, be able to do these kind of basic cone ones. But that was a little bit of a stretch on that one. All right, and it comes out to be 8. On your calculators, you probably get 8 times radical 5 pi all over 5, I think is what it comes out to be. As a decimal, it's like 6.341 or something like that when you solve this for the k. All right, what about the business ones? Any concerns there? You did kind of have the worked out answers, but let's make sure and talk about them if you've got some issues.
Where's the orchestra?
Orcas, yeah.
You seem bitter.
I am bitter. I'm so bitter.
You really
See that tiny?
Squeeze them. Is
It's
that
right
it?
there. That's the
black box.
yeah.
Oh, that's the Black Box Theater. That's where
Yeah,
they're
yeah.
supposed to practice.
That's what it was. Anyway, there is no orchestra. No, it's a black box.
Well, right now it's not finalized. Is this like music and band area in here?
Yeah, and the arts is right behind it.
And art?
Yeah,
That's
arts
art.
is right there.
We have plazas. And this is some open area. No, that's it.
And you can
Staff kind of
section it off.
thing. It can section off, and I don't know. It's gonna be. We have plazas.
Four.
Yeah, that's a plaza student entry.
So
I say,
cover a plaza.
yeah, just like,
And these are all science. Red is science classroom.
and they,
Science lab.
there were some English teachers in the
They're all over the place. There's science rooms. Yeah. Then there's, let's see, this is a second. There's a ninth grade. We'll put them up in a corner. Put them up in the second floor. Never to hear from again.
Yeah, we are. We're separating
That's not a bad idea. I like that idea.
I like
I like it. Contained. We've got a rooftop plaza. We've got a rooftop plaza.
That is cool.
Yeah. That's kind of
Yeah, the entrance is so nice.
Yeah,
it
look
is
at that.
really cool. I mean, in the track and football field are right
Oh,
That's-
they're right next to it? That's weird.
It's yeah.
They're
it's
gonna be
really
chasing
cool.
the ball out to the parking lot and someone's gonna get hit by a car. Wait, are you recording class?
Oh yeah. This is the rooftop plaza kind of right up here.
Oh, that's what that is? Oh.
So it kind of overlooks the field, but then it also like concessions and shared. Like this is the gym, so it is kind of cool.
Yeah.
Swimming pool's right here.
And our,
This is a pool on
our plans for the stage got
the really. Yeah, here's the
forgotten about.
gyms and the pool, locker rooms. So that's all kind of set off. And this is all what student parking is mostly here. Then there's some here. So there's entrances are kind of so the main entrance comes in here or in here, kind of both sides. So I don't know. It'll. Yeah.
We have a golf cart.
What do you mean to get around? Or?
Yeah.
It's actually in the academic area is going to be much closer than here. You know, we're way more spread out here than this one.
Well,
In the academic area, you know, because all of this is
So
set up
where's
here.
like
Now, if you go to PE, you
student
know,
parking is
all pretty much around. This is staff parking up here, and then this would be student, and this would all be student.
Yeah. And then the horseshoe looking thing right there, that all will be parent parking.
This is
There's no
is
student parking area, but there will be 200 is what they're saying right now. 200 places for parents.
but because I think these are like double wide, so they can come and park along there, but then they can also drive through it. They were calling that like the super horseshoe or something. The super
Do you know
super
how-
horseshoe.
Is it going to be easier to get in and out of the parking lot?
Yeah, that's why they have all the parent parking for.
Well, yeah, I think so. I mean, it depends. Eventually, if they get a southern street down here, would make it a little nicer, so everybody's not going this way. I don't know. It'll be interesting.
I would really like.
All right. So anyway, it was,
Yeah, instead of making a sentence.
How about
what were we talking
The
about? Oh,
Skywalker.
No, we
the
were
business package.
Definitely Skywalker.
Anything?
Did you not do it?
Yes.
I had a really tough time setting up 21.
21.
I started it for like 10 minutes
You do that a lot.
I started it for longer, but then I gave up.
and.
Okay, so 21.
21.
Now, the key on 21 is it talks about the units in 25 increments of 25, right? In other words, if there's 300 units sold, then the price was 40, right? Then the price would go up, and then there'd be fewer, and it went down to 275, right? So the price would go up 5, right? Wasn't that what it was? Price would go up 5 for every decrease of 25 that were sold.
So is this pretty much the rent problem?
It
how
pretty
it's
much
set up?
is the rent
Okay,
problem.
okay.
Yeah. The difference is I did it like this. So in other words, if this was 275, so I looked at it. Okay, if it's 300, if you have 300, then 300 minus 300 is 0. So then the price is 40. If it's 275, then 300 minus 275 is 25. But I only want the price to go up 5, right? So that's why I multiplied by 5, or 1/5, or else divide by 5, however you want to think about it. So right, so as x goes down in increments of 25, the price has to go up in increments of 5. So that's where I came up with the 1/5. So I just went through and made that happen that way. So that's the price, little p. And so then you take that. I mean, and then once you get that, you're pretty much done, right? I mean, because then if that's little p, the price, then you multiply that times the number of units, so that's your revenue. And that's what they wanted you to do, right, was just maximize revenue. There wasn't a cost component on this one. So that's your revenue equation. So it's pretty much that rent. Now, some people, I've had people in the past approach this from a linear situation, which is actually exactly what's happening. In having trouble setting up those price equations, typically for us, because we're staying simple with this stuff, well, simple from what it could be in these business examples, all the price situation we have have been a linear situation. If for every occupied unit or every unoccupied unit in the apartment, the rent goes up 30, right? For every $25 decrease in number of units, the price is up 5. And so that's a linear situation. So what you could do is do this, treat it as an ordered pair. You could say, okay, for 300, I'm going to have a cost of 40. For 275, I'm going to have a cost of 45. For 250, I'm going to have a cost of 50, and on and on and on. And then you could treat that as a linear situation. This would be X, and this would be Y, which would be like your price, right? X is the number of units. So then you could start looking at, and you could just do a slope thing. You could say, oh, okay, this is going to have this. If I subtract this, this would be like 45 minus 40, all over 275 minus 300. And so that's 5 over negative 25. That's a slope of negative 1/5. And so then I could do a y equals m times, and then pick one of my points. So let's take that one. Plus, you know what I mean? I mean, and that's really what it is. That's what your price equation is. I mean, if you look at that, it's essentially what I had. Now, ours was flipped around. But if you distribute that negative through there, then that would turn that into 300 minus x, right? Minus x, and then plus 40. And so if you look at that, that is the price equation that I had on the other page. So when you have that kind of linear relationship between number of units and the price, just writing down a few ordered pairs of what the units would be, what the price would be, and thinking of it as just a line equation, that is your price equation. So if you're having trouble setting those up, that's sometimes a way to go. Okay. All right. Anything else? How about the other one? That was kind of like the snowmobile one. I drew it like so. The interesting thing on this one is there really were true endpoints in this situation, right? If you're going to lay this cable, now it's more expensive to go under the water, which makes sense, but it's longer if you go across and then over land. So what's gonna be the cheapest, all right? So I just did a distance thing, this is half mile, and this was, you know, wherever we decide to cross on land, call that x, so that'd make this 6 minus x. So 6 minus x would be the length on land, this would be the length, the hypotenuse here would be the length in the water. So I just did the Pythagorean theorem, and so $8 a foot on, or a mile, or was it foot? No, it would be half a foot across, I guess it would be a mile. So $8 a mile times number of miles, $6 a mile on land times the number of miles on land, 6 minus x. Okay, so that's your cost equation right there. And so you work that out and it comes out to be this. But you do have actual endpoints because you say to yourself, what's the littlest that x could be? Well, if x is 0, that'd be you go straight across in the water and it's all on land. Or what's the most x could be? 6, right? If x is 6, that means you went all the way to here and you went straight across. You didn't go on land at all. Okay, you went only in water. So there really were endpoints, viable endpoints in a problem like that. And I've got them listed there. Okay? So then you got your minimum cost. That's expensive. Wow, $4,000. Okay? But, all right, let's go ahead and let me hand out some things, and then we'll just spend some time, or let you kind of spend some time working. First of all, now not all of this is due tomorrow, because it's, again, I'm not really going to hand out anything new tomorrow as far as homework. I do have one other parametric problem that I might give to you tomorrow as a review, but other than that, this is kind of it. So it'll just be a matter of working some of all of these things. So this is what I would call the arrow problem, and it has a little bit of there's a few on the back, some speed and those kind of things. I give you the equations. I do ask you to think about where they came from, but I just give you the equations. This is that Anton packet I was talking about. Now this packet is, again, from a different textbook. And what I did is I just took a couple of pages from the related rate section in that textbook, and I took a couple of pages from the optimization section in that textbook. So if you look at this, the first page, front and back, says page 274 and 275, those are related rate problems, and I've circled some. Then the next page, you notice, says page 348. That's from a whole different chapter. That was the optimization section, and so those problems are all optimization problems. Okay, so what might be a good thing to do, you know, while you're working today is maybe by tomorrow try to get maybe half of each of those sections done. Maybe work 2 or 3 of the related rate ones, work 2 or 3 or so of the optimization, and tomorrow during class time you could be working on some more. And I'm going to go ahead and give you this because I've got it, just to get it off my hands. This is our other midterm review packet that we're going to do. We're probably a couple weeks away from the midterm. So we haven't quite finished up that other one. We haven't done the free response yet, but I'm going to go ahead and give you this one. So this would be sample 2. Review packet. Yeah, I know. Well,
Oh my gosh.
they died for a good cause. We have, yeah.
That's the
We have
sound
it.
of my heart.
I like
Somebody-
doing these on a separate sheet.
Somebody asked me that when I was carrying this big stack. They said, you know, we have Chromebooks now. I said, yeah, but the problem is when they start writing on their screen as they're doing their math problems. it's probably- Yeah, with Sharpie. It's probably not going to work too
Kind
good.
of
So
like writing on the
I just
computer
haven't.
screen
I mean,
with
could you
a
imagine?
marker.
You really want to type out your work to a math problem? That'd be awesome.
I'd rather not.
That would be awesome. So they're just.
Yeah, I would rather write.
There's just nothing that beats pencil and paper yet at this
There
point.
really
All right, so
I still like
feels like I'm missing something, but as if, let me double check here and make sure there wasn't something really important I was supposed to be saying.
Yes.
Not really. Okay, we kind of finished Luke Skywalker, right?
No,
No,
I
Didn't
didn't
we?
put it to it.
we should we should go through the whole entire thing with Miranda.
Well,
Just to explain it to her.
Anyone else?
you guys can do
No,
it.
no, no, no.
Didn't we get it? I mean, did he make it there on time?
Yeah.
With like A little bit of
a
time.
little bit of time to spare.
Yeah, but it wouldn't be
Right.
interesting if he made it like in 30 seconds.
So I can help you with that one. So the idea is that we would have some work time here. Like I said, probably the first focus might be the Anton packets and related rates and some optimization out of there. Maybe the arrow problem with some parametrics, wherever you think you might need some help. And again, like I say, I'll be here in the morning, I'll be here at lunch, so I can maybe help you, well, I might be here at lunch, I might have to go get some lunch if we're heading over, so I may not be here the whole time. But I'll be here in the morning, and I'll be here for a little bit of class time, and of course, I'll be here Monday morning as well, but, so, right.
So I'll do it like midday, Sunday. What would you do about that?
No book problem. No book problem. Everything goes right now. That's all we know. What do you think last week? Yeah. I had a question about.
For this term.
Well, are you talking about the step or are you talking about the range?
Oh, I guess.
Yeah, the step would be a plot every tenth of a minute, right? Yeah, that's pretty good. Well, this would plot from 0 to 6, whatever seconds, whatever seconds. Okay. Well, it says each second.
But still that doesn't matter.
So a lot of times it's okay to just start with that. And then if it doesn't seem to give you the graph, you can start thinking, oh, okay, well, maybe I need more seconds. Because T is time.
And how can I do it?
You mean what you enter? Okay, then just hit tab.
Hey Logan, did you have some onion rings last night?
And then, you know, and so now,
They were
so
the
you
best
look at
part
that.
of last night.
and-
Like
Yeah,
everything we
because
ordered
X,
was
obviously,
just like.
X is how far the arrow goes this way. Well, it's
It was like-
I just realized that these like buttons together make a call. And I decided.
Mhm.
It kind of looks.